Hello and welcome to the IP Tech Days. I'm Don Pannell, fellow NXP Semiconductors, and my co-presenter is Nicolas Navet, a professor at University of Luxembourg. And together we will present practical use cases for Ethernet redundancy. So we'll first cover some network configurations that we're going to model, and then Nicolas will cover soft error rate modeling that's been done on each of those, and that's been some very interesting information came out of that. And then I'll cover hard error and cost factor considerations, and we'll wrap this up with a summary of what our findings were. Some very interesting things came out of this that were unexpected, so we're quite excited to share this with you. So first, the need. I mean, everybody's been talking zonal networks, and the basis of the zonal network has an Ethernet backbone, which I've highlighted in the figure. And for redundancy, 802.1 CB is the standard there that supports zero recovery time for lost frames, and it's called seamless redundancy. And in this presentation, we're going to look at CB in various topologies and move that CB function around in the network so that these differences can be quantified, and that will help you decide how much redundancy you may need in your network and at what cost. Now, this is not a safety presentation, but the data presented will really help your network and safety teams develop cost-effective redundant solutions. So let's look at these networks that we're looking at. We chose a base network design very much like the figure that you just saw. And then we make minor changes along it, and with the simulation results now you can see if your network's bigger or different, hopefully you can extrapolate the differences. So our baseline is very much like that figure. We have 4 switches that support CB, and we have a legacy talker and listener that don't support CB. So this is the red dot is the CB sequence insertion and split function that splits the single flow into a blue copy and a brown copy. And then this is the CB merge function that ensures that only one copy gets down to the listener. Now, the pros of this configuration is existing end nodes can be used in the same software, same hardware. And hard and soft errors on this backbone are protected. Now, we're defining a hard error as a long duration error, like a broken wire, and a soft error is an intermittent error, like a CRC errored frame. And so that's where these brown and blue wires are the redundant paths in the network. And so even a single switch failure, if it's switch B or switch Y, is protected. Now the cons is the backbone bandwidth is doubled. You can see that you're copying the frame going both ways, actually the whole stream. And I call it double plus because these redundant frames have an R tag or redundancy tag added to them, so it's slightly larger. And then the links to the talker and the listener, these black wires, are not protected against. And single points of failure are not protected everywhere in the silicon. So our network 2, it's identical except we've added 2 switches in the middle, and this was to help us evaluate if the number of hops change the reliability much in the backbone that's being redundant. And then this model, we've taken the CB function out of the switches and put them in the talker and the listener and connected them with dual homing, meaning dual ports. So you have extra protection or flows. Now the advantage here is you get existing switches can be used, and hard and soft errors on the entire path are protected against, including the hard being I could break this blue wire and I would still get the signal down to the listener. And any failure of any single switch is protected, and failure of anything in the blue path and failure of anything in the brown path is protected. The backbone bandwidth is half of that of network 1 because these dotted lines, which were part of the backbone, aren't being used for these flows. So those are available links that can be used for other flows. Now the cons are, it requires dual homed end nodes, and not a lot of devices have dual Ethernet ports. And the end nodes need now to do the CB function, replicating the frames and eliminating the duplicates. And the failure of either the talker silicon or software or the listener talker or silicon is not protected against. So network 4 is an interesting derivation of that concept, where again, you're using the same existing switches, but the talker is single homed. And instead, the frames are replicated and transmitted on the same physical wire in time split differences. So they're temporally or time shifted copies. So again, existing switches and new soft can be used. So we need end nodes does need new software up here, but we can use existing ones. Hard and soft errors on the backbone are protected as before, and soft errors to the link to the talker and listener are protected, but again, hard errors are not. And that's as long as the bit error rate assumption or the noise that's causing a CRC error is less than a single frame, then it will only impact one frame and not the next frame. And if that error is longer in time, then the talker just needs to separate the transmission of those frames for that duration of an error burst, if you will. So that still can protect them. The cons is, again, the bandwidth is the same on the backbone, the double plus, and the end nodes need to replicate and eliminate the frames. So they do have that overhead. Now, again, it only needs to do that for the flows that need this extra protection. So not for every frame going down the wire. And network 5 is our last one that basically is a hybrid. It leaves the link to the listener to be not replicated, so the functions in the bridge, whereas the talker is still doing the temporal replication. And as long as it follows the CB standard, then the bridge can remove the duplicates. So there's a strong desire to want to do that. And so the only change, again, as I've mentioned, is that link difference. But and what does that bring? Well, this was something that popped out at us in looking at this, is that you could actually get different levels of redundancy and achieve this via firmware updates. You could literally start with that network 1 where this is a black wire and this is a black wire because you don't want to change the code in the talker and the listeners. But you still have your redundant backbone with all the CB aware switches. And then with a firmware update, you could move that function to the talker, like in this diagram, and get network 5. And that gets you the protection that's better. And Nicolas will cover that very shortly here. And then later on, you may have another firmware update where you've had the chance to update the code in the listener and move the CB function down there, in which case then you get to network 4. So it's very interesting that over time you can get this added protection just with firmware updates. Now, of course, to make that work, all the switches need to be CB aware and so on to allow that migration. So those are the networks that we're going to be covering. And so now I'd like to pass the presentation on to Nicolas.
Thanks very much, Don, and good afternoon, everyone. Now that Don has covered the different replication solutions that are practical in the context of automotive networks, now let's study what we can expect from them in terms of their reliability. As we will see, what's key is to ensure an end-to-end protection, because a single unprotected transmission on any link along the path will drastically reduce the overall reliability. Now, the kinds of errors that are considered at this stage of the talk are soft errors, typically electromagnetic interferences, EMI, leading to inverted bits, and ultimately to CRC errors, which results in the packet being dropped at the next hop. In terms of the error model, we assume that bit errors are uncorrelated, meaning each bit has the same probability to be corrupted, the bit error rate, and it holds whatever the frame and whatever the link. Well, to us, this simple model is fine to get a general idea of the robustness of the different replication solutions, but we'd like to point out that a more fine-grained model may lead to slightly different results. For instance, the actual cable length may play a role. as the longer the cable, the more likely it is that a CRC error occurs. And for instance, the length of the cable from the end nodes to the switches will typically be less than the cable length between two switches. This error model is for 100 base T1, which does not include error correcting codes, unlike 1000 base T1. We assume without further analysis that this error model would remain valid for 1000 base T1, but that should be studied in more detail. Quantitatively, in terms of BER, both the 100 and 1000 base T1 standards specify BERs better than 10 to the power of -10. In practice, automotive PHYs are much better than that, and for that reason, the following will consider a baseline BER of 10 to the -12, as done in this first experiment, which is to estimate the time between two CRC errors on a single link with respect to the load of the link, the x-axis of the figure. Logically, what we observe is that the time between two errors decreases when the load increases, and the downward trend of the two curves. The packet size plays a role too. The larger the packet, the more likely that it gets corrupted. And on the figure, the blue curve is for the minimum size frame, and the red curve for the max size frame. As an illustration, at 20% load, which could be, for instance, the load on an access link to a backbone, the time between two successive errors is on average 18 hours for the minimum size packet, while it's 3.5 hours at 100% load. Now, before quantifying their reliability, let's get an overview of the 5 replication solutions. What we see is that they rely on different mechanisms. CB-aware switches for 1, 2, and 5, CB-aware talkers and listeners for 3, 4, and 5, dual homing for 3, temporal redundancy for the 4th solution. Some of them have one or several single points of failures, that is, links over which transmissions are not protected at all. Those links are indicated on the slide by the small danger icons. So we see that solution 1 and 2 have 2 unprotected transmissions, solution 5 has 1, while 3 and 4 do not have any such single points of failure. Now, with this information in mind, let's see how efficient these solutions are in terms of packet loss rates. First, what we define as a packet loss is the situation where none of the copies of a packet are received by the listeners. The results shown here holds under the assumption that the BER is 10 to the -12. Practically, to obtain those reliability values, we model the different replication scenarios with the RTWP tool and then developed a Java plugin to the tool that implements a dedicated mathematical reliability analysis. And that's because injecting faults during simulation is not practical with the BRs of automotive PHYs, simply because the CRC errors are just too rare. Now, let's see the protection that solution 1 and 2 offer by comparison with no redundancy. What we observe is that using 1 and 2 allows to increase the reliability by a factor 2 or slightly better with respect to no redundancy. But the packet loss rates are still high, as the order of magnitude is 10 to the -8 or 10 to the -9. We'll see how that translates into time in the next slide. What can be concluded is first that the protection offered by the CB-aware switches cannot make up for the 2 unprotected transmissions on the talkers and listeners end, and second that the number of switches in the backbone, at least for those 2 solutions, practically does not matter, which is good news. Now let's get to solutions 3 and 4, dual homing and temporal redundancy, which are without any single point of failure. As you can see, the protection is much better, 7 to 9 orders of magnitude better than solution 1 and 2 for both of them. And solutions 3 and 4 are almost equally good from the point of view of soft errors. But that's not the case for hard errors, as 3, dual homing, protects against any one hard error, unlike 4, which relies on temporal redundancy and not on spatial redundancy. Finally, the 5th solution that allows the use of a legacy ECU at the listener is a bit better than solution 1 and 2, improvement of a factor of 2, but still that's the same order of magnitude, and that's due to the final transmission from the last switch to the listener, which is unprotected. Now, let's see how the packet error rates translate into the times between two successive packet losses. The data shown in the following is what can be expected for one flow sending a packet of minimum size every 1 millisecond, so typically control messages. So the data is per flow data. We are not considering all the flows of an application. The reliability results are for BRs ranging from 10 to the minus 11 to 10 to the minus 14, and the 5 replication solutions are compared to no redundancy at all. Well, what we see that obviously the BR is a main factor of reliability, so probably it pays off to have good files. Here we see that without any redundancy, a packet is lost once every 1.5 years for a BR of 10 to the minus 14, but the file must be that good. And for instance, at 10 to the minus 12, a 1 millisecond flow will lose one packet every 5 or 6 days on average. Now let's see what our file solutions do. We use color codes here. Red is when packet losses occur every 20 days of functioning or less. Green is for one packet loss at most every 1 year of continuous functioning. And orange is in between. The first and main observation is that solutions 3 and 4 are acceptable whatever the BR, even for 10 to the minus 11. The other solutions may very well be deemed acceptable too, but probably for BRs better than 10 to the minus 13. Of course, acceptable is something which is specific to a certain context. So the table here provides guidelines to select a redundancy solution based on reliability target and the robustness of the file to CRC errors. Of course, it can be specialized, it can be made more accurate with the exact architecture of the network, the exact characteristics of the flows, of the files, and so on and so forth. And this concludes my part, and now I shall hand over to Don for the final slides. Thank you.
Thank you, Nicolas. That was very interesting. So I'm going to cover hard errors and cost factor considerations. Nothing's free. That's for sure. But we still need, redundancy. If you need it, you need to spend some. So let's do this cost effectively. So let's looking at the components. First, you got to create a redundant backbone. And to do that, you typically create a ring, which was originally a daisy chain. So let's say switch B and Z were not connected because you still needed a path to all of the nodes. All you need to do is add this one extra link to create a ring. And that's what basically is done. And that's not too bad for what you get out of it. Now, this seamless redundancy, the standard also needs to be added, the 802.1 CB, in the bridges and the end stations, depending upon where the functions are covered. Now, that does double the backbone's bandwidth for those critical flows. And the cost of CB-aware switches or other silicon is going to depend upon the CB requirements that are needed, like the bandwidth of the ports and the number of critical flows. So those all need to be taken into account too. Now the redundancy on the end stations on these first and last links also needs to be taken into account. As we showed the option A, you can use dual homed end stations. Now that may keep the backbone's bandwidth close to the same, but you need extra links per end station and a lot more PHYs and links in the bridges. So that may not be cost effective. That's up to you in those situations. Now, option B is using the temporal redundancy. And as that was shown by Nicolas, that those were very similar. In fact, the numbers were almost identical. The main difference, of course, this is still subject to a single point of failure of a broken wire here. But again, even T1 here is subject to if it fails. So that these both have the same single points of failure to some degree. Now, the backbone's bandwidth is still doubled, but it also adds more cost and CPU cycles as it is to duplicate those frames. But it's only for the critical flow. So if you can keep that to a minimum, existing CPUs can probably handle that. Now let's look at the cost factor for end sensors and their flows. Well, sensors can be very high bandwidth devices like 8 gig per second cameras. And many sensors are needed too. I mean, 8 cameras is becoming a low number in cars. And can this data even fit on a backbone today? And let's reduce the requirements and see if it fits. So let's go with 6 cameras and 4 gigs per second. So I've cut the cameras down and the bandwidth in half. Well, that's still 24 gigs per second on the backbone. And with redundancy, that grows to 48 gigs per second. And so I asked the question, what year will these Ethernet PHYs and switches be cost effectively available for automotive? I'm not saying they won't. I mean, history shows that it will. The question is when. This bandwidth also does not take into account the additional bandwidth needed for LiDAR and radar and other things that are going on that backbone. So, this isn't the total bandwidth. And then I have a question too. Why double the bandwidth requirements of a sensor when the sensor itself is a single point of failure? And also a camera failure, and I put that in quotes, is more likely due to dirt on the lens versus a silicon or a wire failure. So why not add more cameras such that they overlap? Well, that costs money too, but that may be cheaper than the cost of a more higher speed backbone. Then CB is not needed for these flows at all. And maybe that's not even needed because sensor fusion merges data from many cameras and other sensors, LiDAR, radar, et cetera, to form a whole picture, if you will. And this process repeats continuously such that a soft error, a glitch here, one CRC and one frame of one camera is likely not critical. And even many hard errors like dirt that got up on the lens may allow for continued operation at reduced speeds, and maybe it's a limp home, but it's not a total failure. Now the cost factors for actuators and their flows. Well, after the sensor fusion, a decision is made somewhere in the system on what to do, steer away from a problem or slow down, etc. So turning, braking, accelerating, those are all actuators. They're all very low bandwidth devices. So historically, actuators have been connected using CAN and LIN. So by definition, they're very low bandwidth. And to issue a simple command to speed up, slow down, hit the brakes isn't a lot of data. Thus, doubling the bandwidth of these flows on the Ethernet backbone is totally feasible. And even doubling that bandwidth temporally, on a time shifted basis, on a single link on the backbone is also feasible. I mean, if a CAN link at 2 megabits and you double the messages, that's now 4 megabits. That's not a lot of extra bandwidth on the backbone. So retransmission, this temporal redundancy, is quite often already used today to overcome soft errors on CAN and LIN type of transmissions. So it's feasible and used today. So seamless redundancy, though, still greatly increases the likelihood that that first transmission is received, thus keeping the latency time for this decision to action messages very low. And when I hit the brake pedal or the sensor fusion decision is to hit the brake pedal, I'd like it to get through the first time. So summary and conclusions. Well, hard, persistent errors are easy to see and plan around as noted in the examples. And the likelihood and impact of these errors, wires are likely more prominent versus software and silicons like the last type of error is of course application dependent. That needs to be looked at. Bigger silicon typically is more likely to fail. So soft intermittent errors are harder to evaluate, but the impact of bit error rate has been shown. So 1000 base T1, as mentioned by Nicolas, supports forward error correcting, making the bit error rate analysis much harder, and maybe that's some future work that needs to be done. But rule of thumb that we're following right now is that the numbers presented for 100 base T1 are felt to be a good use for 1000 because 1000 has a much higher bit rate and also has lower amplitude signals between the levels. So that's why FEC, the forward error correcting, was added. Redundancy is not free, and the biggest cost today could be the extra backbone bandwidth. Therefore, apply redundancy only to those flows that absolutely require it. It appears to be more practical to apply redundancy on actuator as compared to sensor flows. End-to-end protection from the talker and a listener results in the highest integrity. You saw those numbers really go up when you even did temporal redundancy. And dual homing with this temporal redundancy both offer that high robustness. And of course, the multi-homing also protects a single hard error. Using 802.1 CB as shown allows development migration from no redundancy to best redundancy with progressive steps, i.e. firmware updates in between. And this allows reuse of existing ECUs without needing to rewrite and redesign everything in one go. Now, of course, the switches need to be CB aware. So thank you very much for your time, and we are open for questions.